Hi, this is Ms. Fitzmars. This video is an explanation of the problem on page 20 of your Unit 8 packet. This is also the 1992 M2 problem. Alright, so in this problem, we have two identical spheres of mass m with a negligible radius, and they are fastened to opposite ends of a rod with negligible mass and a length of 2L. The system is initially at rest, and a bug lands on the left sphere. Okay, so what we want to know first is the torque around the axis immediately after the bug lands. So to figure this out, we need to find all the forces acting on the axis, and we need to draw a torque body diagram. Okay, so I have our object, and we know we have really just gravitational forces. So we have big mg down from here, okay, and that's a distance L away from the center, and also a distance L from the center. We have the mass of our block, mg, and gravity on the bug, which is 3 mg. And then we have some kind of upwards F pivot, okay, or F axis. But we don't care about F axis because we want the torque around the pivot. So I'm going to name these forces, A, B, and C, and to find the torque, we're going to use sigma tau, and so we're going to find the torque from A plus the torque from B plus the torque from C. Okay, and if you use the right-hand rule, you should figure out the torque from C is going to be negative, the torques from A and B will be positive. Okay, so I'm going to put a negative sign in front of the torque from C. Okay, and we're not setting it to MA or I alpha because we just want to know the net torque. We don't yet want to know the acceleration. Okay, so what we're going to use is the equation for torque. So we know that in general, torque is FR sine theta, and we can also see that all of the forces here are acting at a 90-degree angle to the line connecting the force with its pivot point. And so all of our sine thetas in this situation will be equal to 1, since sine of 90 is equal to 1. Alright, so we have the torque from force A, and that will be 3 mg times the distance from that force to the pivot point, which is L. Okay, and then for torque B, we're going to add mg, and again, the same distance, L. And then for torque C, we have minus, the force is mg, and again, the distance is L. And that is our net torque. So we have 3 mgl plus mgl minus mgl. And so our total torque is equal to 3 mgl. Alright, so in part B, it asks us to find the angular acceleration, so that's our alpha, of the rod sphere bug system immediately after the bug lands. And to figure this out, we can use sigma tau. Okay, the net force is equal to, the net torque is equal to I alpha. Remember that this is our analog of sigma f equals ma. Okay, so we have the total torque. We know that this is going to be 3 mgl. What we have to find before we can calculate alpha is the moment of inertia of this system. So in order to calculate I, we have to look at the picture a little bit more closely. So we have, basically, on this picture, an axis of rotation. 3 different point particles. Okay, so I'm going to name them A, B, and C. So the bug is particle A, the dot that the bug is sitting on is particle B, and this other dot is particle C. So we know that if we want to know the total moment of inertia, that's going to be the sum of our individual moments, IA plus IB plus IC. Okay, we also know that the moment of inertia of a point particle is equal to mr squared. Okay, so our total moment of inertia that we're going to plug into torque equals I alpha will be the mass of A times RA squared plus the mass of B, RB squared, plus the mass of C, RC squared. Okay, now we know that the mass of A is 3m, okay, and the distance from the pivot point, or the center, is L. So we have 3m L squared. B just has a mass of m. Again, it's a distance L from the pivot point, so we have plus ml squared. And the other sphere on the other side, again, has a mass of m and is a distance, even though it's on the other side, that is still L away from the center. Okay, so if we add this all up, we have 5ml squared. And what we're going to do is we're going to take this and put it in for our I over here. So we have 3 mgl equals 5 ml squared alpha. Okay, and we can see our m's will cancel out, and one of our l's will also cancel, and we end up with alpha is equal to 3g divided by 5l. Okay, so that's part B. Now, as soon as the bug lands on the sphere, the whole thing is going to turn around. Okay, and so in part C we want to know by the time the bug reaches this bottom point, what is its angular speed going to be? And what I want you to do, even if you haven't gotten this far in the problem by yourself, is I want you to take a minute and I want you to think, what can I use to solve this problem? So can I use sigma tau equals I alpha? Can I use conservation of angular momentum, sigma L naught equals sigma L? Or can I use conservation of energy? Those are really the 3 tools we've been working with. I want you to pick one of them and try to justify to yourself in the margins why you would pick that one and why the others don't make sense. Alright, so now that you've thought about that, we're going to talk about these one by one. The first option, which is to use sigma tau equals I alpha and then use rotational kinematics, that actually isn't going to make sense. And the reason that's not going to make sense is that as the direction of the whole apparatus changes, what you're going to find out is that the total torque changes. Okay, so if our torque is changing, then alpha, our angular acceleration, is going to change, and what that means is rotational kinematics will not be valid. Okay, because we can only use those equations when we have a constant angular acceleration. Now let's think about conservation of angular momentum. So it turns out we can't use that as well, and the reason is there's a net torque on the system. When there's a net torque on the system, we can't use angular momentum. And so the only thing left is conservation of energy, and there's no heat, there's no work in this situation, so conservation of energy is completely true. Okay, so let's take a second, and I'm going to draw the initial picture again over here. I have the bug, which has a mass of 3m, and we have our other mass. So we have 3m, m, and m. Okay, all of the masses are a distance L from the center point. And what I'm going to do is I'm actually going to draw this on the same exact axis . And what we can think about is if the original axis, so this orange line, is your height is equal to 0, then at the beginning, you pretty much have no energy. The thing is not moving yet, it has no height, so sigma E naught is 0. Now, at the end, we have kind of this tricky situation where one of our masses has gone up and one has gone down, but they both separately have UG. And they're also both separately moving or moving together. And this whole thing is not moving, but they are spinning, so that's rotational kinetic energy. Okay, so what we can say is at the beginning, if we're setting sigma E naught is equal to sigma E, at the beginning we have no energy at all. At the end, and again, just for convenience, I'm going to name our objects. Let's say this is A, the bug is B, and this other blob is C. Then at the end I have to do UGA plus UGB plus UGC, okay, and also plus rotational kinetic energy. Okay, so we have 0 equals A, mass A, so that's mg, and the h is length L, so mgl. Okay, for mass B, and mass B is the bug, so we have 3m g, and it is L below, so we could say its height is negative L. Mass C is this blob that just has a mass of m, so we have mg, and again, height of negative L, plus 1/2 I omega squared. Okay, so we can go ahead and add up our like terms. We have mgl, essentially minus 3mgl minus mgl, and this gives us 0 equals minus 3 mgl plus 1/2. And in for my I, if we think back to part B, we know I is 5 ml squared. So I have 1/2 times 5 ml squared. And omega, since in general V equals omega R, omega will be V squared over R, or V over R, but actually we're just trying to solve for omega here, so we can just leave it as it is. And I'm going to take this line and move it to the next page. And I'm solving for omega, so I want to move this minus 3 mgl to the other side. So I have 3 mgl at this point is equal to 5/2 ml squared omega squared. Okay, so hopefully you can see I can get rid of my m's. I can also get rid of one of my l's. And I have 6/5 g over L is equal to omega squared, or omega is equal to the square root of 6g over 5L. Alright, in part D, I want to know the angular momentum of the system. It's just a straight calculation. I know that angular momentum is L, and that's equal to I times omega. So then I have L is equal to I, which was 5 ml squared, times omega, which was the square root of 6g over 5L. And I'm going to pull all of this inside of the square root. So I have L is equal to the square root of 25, because I'm squaring the 5 to bring it inside the square root, m L to the 4th, and I still have 6g on top, divided by 5L. Okay, so the 5 and the 25 cancel to just get 5. Okay, L cancels with L to the 4th, so we now just have L cubed, and we end up with our angular momentum is equal to the square root of 5 times 6, which is 30 g L cubed m. Finally, in part E, we want to know the magnitude and direction of the force that has to be exerted on this bug to keep it from being thrown off the sphere. So first of all, let's draw a force body diagram of the bug. And we know that, of course, gravity is pulling down on our bug, so we have Fg. And then we have some kind of upwards force. Maybe it's stuck, its feet are sticky, and it's stuck to the sphere, but we have some kind of upward force keeping the bug stuck to the sphere. Now, we know because this bug is going around in a circle that sigma Fy equals MAY, and that AY has to be equal to AC. It's going around in a circle. So F up, which is what we're trying to find, minus Fg, and by the way, this is going to be 3mg. So F up minus 3mg is equal to, and I'm going to put a 3 in front of our mass because our bug has a mass of 3, AY. And for AY, of course, I'm going to put in V squared over R. The thing is, I don't know what V is, but I do know omega, and I know that in general V is omega times R, the radius of the circle something's going around, which in this case is L. And I also know I can replace this R with an L based on the letters I've been using. So I have F up minus 3mg equals 3m omega squared L squared divided by L. Okay, one of my L's is going to cancel out. And what I'm going to do is I'm going to take my old expression for omega that I found in part C, and I'm going to take this and put it in right here. So now I have F up. I'm also going to bring this to the other side by adding it, is equal to 3mg plus 3m. Omega squared is just going to be everything taken out of the square root, so 6g divided by 5l times L. Okay, now these two L's will cancel, and I have F up is equal to 3mg. Notice I can factor out an m and a g from each term. 1 plus 6/5. Okay, we know 1 plus 6/5 is, of course, 11/5, so we have 11 times 3, which is 33/5 mg. And this is the force with which the bug has to stick to the sphere in order to not fall off.